The next chapter we're going to cover, the next two chapters actually, are just about the elements themselves. No problems, you guys. I know that makes you worried, but anyway, I'm going to go through them kind of quick because there's a lot of slides and there's not a lot of problems or anything like that that I have to show you how to do. So I'm going to be kind of speedy, but we'll get through this chapter. This one's nonmetals and the next one's transition metals. Okay. So when we're talking about descriptive chemistry, okay, we're going to talk about how elements occur in nature. A lot of elements you won't find in pure form. Okay. Most of the time we have to take elements and we have to isolate them from their sources, whether it be ores, rocks, combined with oxygen, something like that. Okay. And then we also, when we use descriptive chemistry, we talk about how they're used. That's an important thing. The emphasis when you talk about nonmetals is hydrogen, oxygen, nitrogen, and carbon. And those are the big four elements. And you'll find them in all living things. Carbon is one of the most common because it's in all organic compounds, things like that. Okay. The other thing when you're using descriptive chemistry, you look for trends. It helps you memorize things about the elements. Okay, how they're classified, gives you the trends as far as what. When I talk about trends, I'm talking about like their size, their radius, things like that. Okay, so here's a trend for metals, nonmetals, and metalloids. Remember, the only nonmetal that hangs out with the metals is hydrogen. But you can see we have increasing ionization energy, the energy required to form ions, decreasing atomic radius, increasing electronegativity. All of these things we talked about before, and they're listed in your book. Decreasing metallic characters. So the first column is the most metallic, and then so on and so forth. And then you can look over here. You can't see all of it, but this is decreasing ionization energy as you go down the column, increasing atomic radius as you go down because you're adding more levels, more layers, decreasing electronegativity. In other words, that's how much they want electrons. The most electronegative is right here, that's fluorine, and increasing metallic character as you go down. So the most metallic would be down here because this is the column where they're most metallic, and then you go across. Okay, those are trends. When we're looking at nonmetals, oxygen is one of the most important. Obviously, life depends on it. If we can't have oxygen, we die. And oxygen is really is an important component of water. Another thing that if we don't have, we die. Okay, we have a lot of oxygen and water in our environment, which is nice. 1/3 of our chemical reactions usually involved oxygen or water. Okay, a lot of our stuff, in order for a reaction to occur, they have to be aqueous, they have to be dissolved in water, and so on. When we talk about our acids and bases, we have protons being transferred. So we have a weaker Bronston-Lowry acid and a stronger base. And again, remember, it transfers one hydrogen over, and that's how you can tell it's the conjugate base. We have combustion, where we take some sort of carbon fuel, we burn it in oxygen. If there's no oxygen, it doesn't burn, and we end up with carbon dioxide and water. Okay, nitrogen, you won't find too much as nitrogen. Most of the time you find it as N2. And our air is 80% nitrogen, or 79, sorry. But it forms special nitrogen oxides in cases. If you want more nitrogen in your environment, one of the things that'll fix it is lightning. That's why after a storm, it looks like your grass has grown, because it probably has, because it's freed the nitrogen. Okay? Hydrogen is the most abundant element in the universe. Number one, good old hydrogen. Although 75% of the mass of the universe, it's only 0.87 of the Earth's mass. So there's a lot more hydrogen in the universe than there is on the Earth. One of the reasons why its mass isn't much, there might be a lot of hydrogen, but remember, hydrogen is very light. And most of the hydrogen is in water. Okay? So even though we have a lot of hydrogen, if you go by mass, there's not a lot because, again, it doesn't weigh very much. It's the lightest of all the elements. If you look at all the stars, those are all made out of hydrogen. So in the universe, it is by far the most abundant element. Okay. Its name comes Greek from water producer, hydro. Hydro means water. Okay. And so because you take water or water producer, because it produces water when it's burned in air, you take water, hydrogen and oxygen, and you end up with water. But again, hydrogen comes from the hydro means water. Okay. Isotopes of hydrogen, there are 3. And again, remember an isotope has the same number of protons, but different number of neutrons. Okay, protium, where it doesn't have a nucleus, it only has one proton, that's 99.98%. So most hydrogen is hydrogen with one proton and no neutrons. Deuterium its mass is 2, which means it has one proton and one neutron. You can see it's a small amount. It is not radioactive, okay, but they often call it heavy hydrogen water, okay, because of what else it combines with. Okay, tritium, which is hydrogen 3, which means it has 2 neutrons and 1 proton to get its mass. It is radioactive. Okay, you can see its half-life is 12.3. If it's a beta emission, that means it gives off an electron. Okay, so those are the 3 isotopes. The difference in masses between hydrogen 1 and hydrogen 2 results in a little bit different physical properties. Okay, hydrogen 2 and 3 are often used to label compounds to follow chemical reactions. Okay, and again, there's not a lot of it, so those are used in like radio tracers. Okay, but most of our hydrogen is the hydrogen we're used to, good old hydrogen with 1 proton, and that's it. Okay, some of the things about hydrogen, it's unique. There is no other element like hydrogen. It doesn't belong in a group. I mean, it's in the alkali metals, but it's not. It's a non-metal. It's the only non-metal hanging out over there. So it doesn't belong in any group. It's an entity by itself. Okay. It has very low melting point and boiling points. Okay, so it's a gas at room temperature. Okay, it's a diatomic, one of the diatomic elements, but again, there is no other element that's like hydrogen. Okay, hydrogen has a very large bond enthalpy. If you remember that, that's the heat. Okay, it reacts slowly, but when it's activated, the hydrogen atoms react quickly, and they're very, very exothermic. Okay, to give you an idea, the Hindenburg, if you've ever watched when the Hindenburg, the first blimp came across and it caught on fire, it was filled with hydrogen and it was kaboom. Okay, now they fill blimps with helium so they don't get any more kabooms. Okay, but they're they form strong covalent bonds with other elements. Remember, they only need 1 electron. They need 2 total. Remember, they have 1 to share, and they only need 2, whereas everybody else needs 8. But if you put hydrogen and oxygen together, okay, they can make a liquid fuel that they use in rocket engines. So they're very, very explosive. Okay. When you want to produce hydrogen, okay, they make it in labs, smaller quantities. When you take hydrogen and you use an active metal, like active metals would be the alkali metals, the alkali earth metals, or whatever, you're going to end up with an acid. Okay, and you can see here's methane plus water, and you get carbon monoxide, which is not so good, and hydrogen gas. Okay, if we take carbon monoxide, so this is kind of a step-by-step over, but if you take carbon monoxide and add water to it, then you get carbon dioxide and hydrogen. So this is another way of getting hydrogen. Okay, or you can take just solid carbon and water, and you end up with hydrogen and carbon monoxide. So in both those cases, you got carbon monoxide, which you got to be careful of, but hydrogen, hydrogen, hydrogen. This is the one where you'd get the most. Okay, if you commercially produce it, it's usually from a reaction of methane, and then they steam it. Okay, the water there, the gas is 111. That's pretty high. Okay, so in order to get the Celsius, it should be on this side, the little thing. Sorry about that. That's the most common. Or they take carbon and they take water and get it. But you can see you get more when you use the methane. You get 3 moles as opposed to 1 mole. Okay. Okay. Another way they do it is you can take water and pass an electric current through it, and you could collect hydrogen and oxygen. The problem is the energy you get from burning the oxygen and hydrogen you collect is much less than the energy you had to put in to get them. So it's not a very energy efficient method. You waste energy when you do electrolysis. Okay. So the uses of hydrogen, about half of all hydrogen is produced, is used in what they call the Haber process. And the Haber process is how we make ammonia. Okay, ammonia is huge. They use it in the egg industry for fertilizers and all kinds of other stuff. Okay, most of the remaining hydrogen is used in what they call cracking, producing lower molecular weight hydrocarbons. It shouldn't say cracking. In our area, we call it fracking. Okay, so hydrogen is basically used to synthesize ammonia or in fracking. Okay. It's also used to produce methanol, which is a low-grade alcohol. Okay. And you can see carbon monoxide plus hydrogen gas, and you get this is methanol, CH3OH. Okay. So the hydrogen economy, they called it. Oh, say if you take hydrogen gas and oxygen gas and produce water, you can see the change in energy, the heat, it's negative, so it's exothermic, 483.6. That's how many kilojoules of energy you get. Okay. So using hydrogen as a fuel has some distinct advantages. Okay. Its reaction with water is highly exothermic. It releases a lot of energy. The only product is water. I mean, talk about no pollution producing water. It has low mass, so it gives high density energy. So for the amount of hydrogen you have to use when you burn it, you get a lot of energy from it. Okay. So hydrogen economy, what they're saying is using hydrogen as a source of fuel. Okay. What's the problems? Okay. To get hydrogen gas takes energy. Sometimes you don't get as much energy out of burning it as it took to get it. So that's a problem. If you store hydrogen fuel, it takes a lot. So they need large volumes of hydrogen. Well, let's say you have a car that's run by hydrogen. Where do you store it? It's not like, it's not a liquid, so it's not as easy to put in your car as like a gasoline. Okay, and one of the biggest problems with hydrogen is very, very, very explosive when it's exposed to air. So you have to really be careful with it. But it's a very clean burning fuel. Only problem you have the only byproduct you have is water. So no pollution when you burn hydrogen. Okay, here's some of the things, and there is a move toward hydrogen economy. It's renewable. Here's some of the places, the way they get it. Electrolysis, we talked about, not a great one. Biomass, natural gas. So there's all kinds of issues in the hydrogen economy, good and bad. One of the good things with a hydrogen economy is you'll find it in photovoltaic cells, solar cells, and in hybrid fuel cells. So if you have a hybrid car, it's basically using the hydrogen economy. So, it has some very good uses, and it has some not so, it has some disadvantages. Okay. When you have hydrogen combining, you get what they call hydrides. Okay. Hydrogen, remember, changing the ending to IDE. So in other words, it is the cation. It's not listed first. It's not the anion. It's listed second. So you have ionic hydrides, you have metallic, and you have molecular. Okay. Ionic hydrides, again, now hydrogen is going to be -1 instead of +1. We're always, you're always kind of think of hydrogen as +1, but it can also be -1. And that's when it's a hydride. Okay. So if you take an alkali metal and hydrogen, or the alkali earth metals, calcium, strontium, barium, you're going to get a hydride. And there's down here, here's calcium. And it forms, a hydride is very, very basic. You can see this is phenolphthalein, and phenolphthalein turns pink in the presence of a base. They're very strong bases, and they're very strong reducing agents. Okay. They react readily with water and oxygen. So you have to make sure you store them from where they're free from moisture and air. So it's can be an issue storing them. You can't just set them on the shelf because they're going to be exposed to air, and then they could explode. Okay. Metallic hydrides are formed between hydrogen and transition metals. Transition metals like copper, iron, the ones in the middle. They often form what they call non-stereometric ratios. So in other words, weird numbers. Here you can see titanium, hydrogen 1.8. That's not something, we're always used to whole numbers, but it's kind of a weird ratio that can occur with these guys. They do become very electrically, they're really good conductors of electricity, and they have very strong metallic properties. So these are hydrides of the transition guys. Okay, here are some molecular hydrides. They're formed between hydrogen and nonmetals or metalloids. Okay, they're usually gases. So when we're talking about hydrides of hydrogen, we can have the ionic, which is the first two groups of metals. We can have the transition, and then we can have the molecular. And molecular would be forming molecules. These are with the nonmetals. Okay, their stability of nonmetal hydrides decreases down a group. So these guys are the most stable. These guys are the least stable. And we're going to run out of time, so we're going to quit right there. Okay.